Welcome to Math 201. In this lesson, we're going to discuss limits, section 1.8. Okay, so we're going to talk about limits. The intuitive definition of a limit is the limit of a function f of x as x goes to a value c is the value the function approaches as you evaluate f of x closer and closer to c. Or even more intuitively or succinctly is to say, does the function, what value does the function want to take as equals c, to take at x equals c? So I'm going to draw a picture, a couple of pictures to help us wrap our brains around this. So here's a function, and this is x equals c. And if you go up to the graph, the value of the function at c is f of c. Okay. And when we're talking about a limit as x approaches c, I don't actually care what the value of the function is right at c. I'm curious what the value of the function is approaching as the x values get closer and closer to c. So imagine you have like a little ant standing on this curve. And there's another one over here, and they're both marching towards, marching along the graph, getting closer and closer to x equals c. They're getting closer and closer to the point c comma f of c. Okay, so the x values are getting closer and closer to c. The y values are getting closer and closer to f of c, and we're going to call that value L for limit. Okay. Now I'm going to draw a similar graph, but slightly different. Okay, it's going to look just like this one. Okay, similar. Here's C, but we are going to have a big old hole. Okay, right here at x equals C, there's a hole in the graph. Okay, so this value is no longer f of c. Okay, so the function value at c is not f of c. Doesn't have a value there. Okay, so we can still call it L. It's still approaching a value. Okay, as my x values, as my little ants march along the curve, getting closer and closer to x equals c, the y values are getting closer and closer to this value L. This is the function value. This is the value the function wants to take at c. It's L. Okay, even if there is no function value there. Okay, it still has the same limit. It's still approaching the y value of L. Okay, recall this function from last class. What is the limit of g of x as x approaches 0? I think it will be helpful if I draw a picture of this graph before we try to answer the questions. Okay, so I have the function graphed. What is the limit of g of x as x approaches 0? So here's x equals 0 right here. Set the x-axis. And so I want to put a tiny ant on the graph, one a little to the right and one a little to the left of x equals 0. So I've got these little ants. Put arrows to indicate that they're marching towards x equals 0. So we've got a little ant right here and a little ant right here. They're both on the graph, one a little to the left of 0 and one a little to the right of 0. And they're both marching towards x equals 0. What y value are they marching towards? Okay, as they march along the graph towards x equals 0. The y value they are approaching is 1. Okay, and the notation we use is the limit as x approaches 0. So as the x values get close to 0, the limit of g of x is 1. Okay, same function, but this time I want to know what is the limit as x approaches 1. So this one's a little bit trickier because 1 is where I have the discontinuity. Here's x equals 1, and I have this jump here. Okay, so let's see if I can approach it the same way. So here's x equals 1. That's where I'm interested in. I'm going to put a little ant on the curve a little to the left of 1. So here's a little to the left of 1. Go up to the graph, and we'll put a little ant, and it's going to be marching towards x equals 1. And then go a little bit to the right of 1, go up to the graph, and put an ant marching towards x equals 1. So from the left, okay, over here, my little ant, as it approaches x equals 1, the y value is approaching 3. Okay, it's getting closer and closer and closer to y equals 3. But over here, as my x values get closer and closer and closer to 1, my ant is marching along the curve. The y value it's getting closer to is 2. So here I would say the limit is sort of 2 and 3, but um, we have decided mathematically that if you are approaching a different y value from the left and from the right, we say that the limit actually does not exist. Okay? DNE for short, does not exist. So our notation for this is that now I can use notation to be clear that what the limit from the left and the limit from the right are and that they're different. Okay, so we can say the limit as x approaches 1. And then to indicate from the left, we put a little negative sign right here. That means we're approaching 1 from the left side of 1. So we're talking about this little ant right here. We went a little to the left of 1, put an ant on the graph, and it is marching towards 3. Okay. But then the ant that we started on the graph a little to the right of 1, so we say the limit as x approaches 1 from the right of g of x is 2. This is your first activity for lesson 1.8. I would like you to pause the video, work through this activity, and then come back and watch the rest of this video um, if needed. Okay, let's go ahead and answer these questions. So the limit as x approaches 7 of h of x. So first we identify x equals 7 along the x-axis. I'm going to put a little ant to the left and to the right of x equals 7 on my graph. I like to use arrows to show which way they're marching. They're both marching towards x equals 7. What y value are they marching to? And it looks like the y value that they are marching towards is a 2. Okay, the limit as x approaches 3 from the left. So first we find 3, it's right here. I just need one ant a little bit to the left because we're only approaching from the left. As this little ant marches along the curve towards x equals 3, it is approaching a y value of 1. Okay, what about the limit as x approaches 3 from the right? Okay, so here's 3 again. And this time I'm going to put a little ant on the graph just to the right of 3. And as this little ant marches along the curve towards x equals 3, it's approaching a y value of 4. Okay, and then because the limit as x approaches 3 from the left and the limit as x approaches 3 from the right are not the same value, the limit as x approaches 3 does not exist. All right, how about the limit as x approaches 9 from the right? Okay, so here's my 9. I'm going to go just to the right and put a little ant on my graph. And I put a little arrow indicating that it's moving towards the 9. And this looks like it's an asymptote. This looks like it just keeps going up and up and up forever. And I would say that that limit is infinite. Okay, we have a few properties of limits that will be helpful to use when we are trying to compute limits. First, if b is a constant, then the limit as x approaches c of b times f of x is just going to be b times the limit as x approaches c of f of x. Okay, so you can take the limit of f of x and then multiply by the b, okay, instead of doing b times f of x first. If you want to take the limit of a sum of two functions, you can break them apart into two separate limits and then add them. So we can do the limit as x approaches c of f of x plus the limit as x approaches c of g of x. That's also true for subtraction. It's also true for multiplication. Um, it's also true for division, assuming the limit of the denominator is not zero, because we don't like to divide by zero. Okay, so this says the limit as x approaches c of f of x divided by g of x is the same as the limit as x approaches c of f of x divided by the limit as x approaches c of g of x. Now, if k is a constant, the limit as x approaches c of k is k. The function is always k. The y value on a function of a constant function is always k. So wherever you put the ants, the y values are never changing. They're always k. And if f is continuous, then the limit as x approaches c of f of x is f of c. Okay, so you can just use the y value of the function when it's continuous. So if I just draw a little picture to make this clear, here's c. Because this is continuous, the limit that I approach when I march towards x equals c from the left and the right is f of c. Okay. The only time it wouldn't be f of c is if I had a hole or a jump or an asymptote here. Um, but those are examples of discontinuities. So if the graph is continuous, you can just plug in the value c into the function to get the y value that is the limit. Okay, so first example, the limit as x approaches -1 of x squared plus 3x plus 2. So the first thing I should try is just to plug in a -1. Like if this is a continuous function, then I could just plug in -1 and get the y value to evaluate the limit. However, when I try to plug -1 into this function, the denominator becomes 0, which means this actually is not continuous at x equals -1. So I can't put -1 in here. I get a 0 in the denominator. So let's just note that. Can't plug in x equals -1 because the denominator will be 0. Sad face. Okay, so what I can do instead is say that the limit as x approaches -1 of x squared plus 3x plus 2 over x plus 1 is the same as the limit as x approaches -1 of, let's factor and cancel. So x squared plus 3x plus 2, that factors to x plus 2 times x plus 1 over the denominator x plus 1. And then my x plus 1's cancel. And I get the limit as x approaches -1 of x plus 2. And now I don't have a denominator to worry about becoming 0. I can just plug a -1 in because what I have now, x plus 2, is a continuous function. So this is going to become -1 plus 2, which is 1. Okay, so this is an example of good notation. Okay, an example of bad notation for the same problem would be to say that x squared plus 3x plus 2 over x plus 1 equals, okay, x plus 2 times x plus 1 over x plus 1. So far, this is fine. But then when I do the canceling part and I say this equals x plus 2, this is not always true. Okay. It's almost always true, right? It's true for every x value except x equals -1, because x equals -1, you cannot plug into this one, but you can plug into this one. Okay, so if I leave off of the limits, right? If I leave off these limit notations and just write this without the limits, this is technically not good notation because this is not always true. If we write the limits, this is true because we're not concerned with what happens exactly at -1, but only when we're very, very close to x equals -1. Okay, and when we're very, very close to x equals -1, this expression and this expression are equal. This is your second activity for lesson 1.8. Please pause the video at this point, work on this activity, come back and watch the video if necessary. Okay, the limit as x approaches 2 of x squared plus 2x plus 1 over x minus 1. First thing we should always try is to just plug in the x value, the that I'm taking the limit for, x approaches 2. I want to just try plugging x equals 2 into the function. The only time that that's not okay is if you get a 0 in a denominator, okay? Um, so what I'm going to do is try to just plug in the 2. So I'm going to have 2 squared plus 2 times 2 plus 1 over 2 minus 1. I'm good. No 0 in the denominator. I can just calculate this. So this is going to be 4 plus 1 is 9 over 1, which is 9. Okay, next one, I'm going to try the same thing. Try to plug in the negative 1. Okay, so I have negative 1 squared plus 4 times negative 1 plus 3 over negative 1 plus 1. And oh dear, 0 in the denominator. Okay, so I can't do that. I'm going to try my factor and cancel technique. So this is going to be the limit as x approaches negative 1. Factor the numerator. That would be x plus 3 times x plus 1 over x plus 1. That's so nice because now my x plus 1's cancel. So this is the limit as x approaches negative 1 of x plus 3. And now I can plug the negative 1 in. So I have negative 1 plus 3, which is 2. The limit as x approaches pi over 2 of the tangent of x. Okay, so what is the tangent of pi over 2? So let's draw a unit circle and see if we can remind ourselves of a little bit of trigonometry. Unit circle. This is pi over 2 right here. Pi over 2, and the coordinates of this point are 0, 1. Okay, so the tangent of pi over 2, remember, is y over x, which would be 1 over 0, which is undefined. Okay, so I cannot just plug the pi over 2 in because you get 1 over 0, undefined value. So instead, I'm going to have to think about what is happening to the value of the tangent as the angle gets closer and closer and closer to pi over 2. So I'm going to erase this, and I'm going to put an angle that's really close to pi over 2, right? So I am towards pi over 2. So imagine this getting closer and closer and closer. This is going to be approaching pi over 2. Okay. So my y values are getting closer and closer and closer to 1, and my x values are getting closer and closer and closer to 0. So I'm going to say that this is approaching, the numerator is approaching 1, the denominator is approaching 0 through positive values because the x values of these coordinates are all positive values that are getting closer and closer and closer to 0. So 1 divided by teeny, 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 tiny number is a really, really, really big number. Okay, so this would be infinite. Right? However, that's only approaching pi over 2 from this side, right? I can also approach pi over 2 from over here. So here's an angle that's a little bit bigger than pi over 2, and we can get closer and closer to pi over 2, like from this side. Okay. So those values are the numerator, oh, the y value is approaching 1. The denominator is also approaching 0, but these x values are negative, right? To get to this point right here, you go left and then up. So the x coordinate of this point right here is negative. So they are getting closer to 0, but they're going through negative values. So if you divide 1 by something very, very, very small, very close to 0, you get a really big number. So that's going to get bigger and bigger and bigger, but it's negative because it's 1 divided by negative 0.1, negative 0.01, negative 0.001. So this limit does not exist, okay? Because from this side of pi over 2, it's approaching infinity. But from this side of pi over 2, it's approaching negative infinity. So this limit does not exist. Okay, now I want to take a limit as x approaches infinity. So what is happening to the y values of this function as the x values get bigger and bigger and bigger and bigger? So I like to think of this as two functions that describe money in a bank account. Um, so picture a large number, a million, right? Say you have $1 million, okay? And what you're going to do is you take that $1 million and you're going to raise it to the fifth power. That means a million times a million times a million times a million times a million. Like that is a ginormous number, incomprehensibly large number. Okay. Which absolutely dwarfs a million squared, right? A million squared would be a one with 12 zeros after it. I don't even have a name for that. It's so big, right? But a million to the fifth is going to be a one with 30 zeros after it. Okay. So like so big that it's completely dwarfs. And then compared to this one lonely singular dollar, like that means nothing. Okay. Or a million times a million times a million times a million times a million compared to just a million, right? This is so much bigger. Okay. So I only really need to look at the highest power of x when I'm looking at really, really big x values. So 3x to the fifth over 2x to the fifth. Those limits are going to be the same because the fifth power is going to so completely dominate. It's just so much bigger than the x squared that the x squared is like loose change in your couch, like compared to a million to the fifth. It's so big. So I'm just going to ignore the lower power x's and only look at the highest power. Okay, and then my x to the fifths can cancel. And so this is just going to come out to the limit as x goes to infinity of 3 halves. And we had one of the properties of limits was that the limit of a constant function is just always 3 halves, right? Because so y equals 3 halves would be this graph right here. Goes on forever at 3 halves. So if I put a little ant on the graph marching to the right, it just keeps going to the right, right? So my as my x values go towards infinity, my y values are just staying at 3 halves. For the problems below, we're going to let f of x be this quadratic function, 2x squared minus 4x plus 3, and g of x be this piecewise function that's 1 minus x squared if x is less than 0, and x minus 1 if x is greater than or equal to 0. Compute the following limits. If possible, you may find it helpful to sketch g of x. So let's go ahead and sketch g of x together before we try to answer any questions. Okay, so 1 minus x squared if x is less than 0. So if you were to put a 0 in here, you would get a 1. 1 minus 0 squared is 1. So 0, 1, but I'm putting open circle because it's not actually defined there. And then this would be a parabola that opens down. It's going to cross the x-axis at -1. Okay, and then x minus 1 for x is greater than or equal to 0. So if I plug in 0, I get -1. And that's going to be a line with a slope of 1. So it goes like that across the x-axis at 1. Okay, so what is the limit as x approaches 0 from the left of g of x? Okay, so first I identify 0. Okay, so here's x equals 0. And I want to approach from the left. So I go just a tiny bit to the left, and I'm going to put a little ant on my curve. And that little ant is going to march along the curve towards x equals 0. And the question is, what y value are we approaching? Okay, so it's just going to keep going along the curve. And it looks like the y value that it's approaching is 1. Okay, so now I want to do the limit as x approaches 0 from the right. So I identify x equals 0, move a little bit to the right, and put an ant on the curve a little bit to the right of 0. That ant is going to be marching towards x equals 0. So I can just keep drawing these little arrows. It's walking along the curve. Looks like the y value we're approaching is -1. Okay, next I want to take the limit as x approaches 1 of f of x plus g of x plus 4. So one of my properties of limits said that I can take the limit of each of those three functions separately and then add them together. So this is going to be the limit as x approaches 1 of f of x plus the limit as x approaches 1 of g of x plus the limit as x approaches 1 of 4. Okay, so the limit as x approaches 1 of f of x is a polynomial. Polynomials are always continuous, so I can just plug 1 into this formula. So if I plug a 1 in here, I'm going to have 2 times 1 squared minus 4 times 1 plus 3. So that's my limit as x approaches 1 of f of x. The limit as x approaches 1 of g of x, so I'm going to go to my picture of g of x. Here's x equals 1. Go a little to the left and a little to the right. And as those two ants are marching along the curve towards x equals 1, the y values are approaching 0. And then the limit as x approaches 1 of 4, remember, that's just a constant function at a height of 4. And as x approaches 1, my ants are marching along the curve towards y equals 4 because the y values are always 4 on a constant function. Okay, so this comes out to 2 minus 4, which is -2 plus 3 is 1 plus 0 plus 4, which is 5. Okay, the limit as x approaches 2 of f of x times g of x. Well, our properties of limits say that you can take the limit of f and the limit of g first and then multiply them. So this is the limit as x approaches 2 of f of x times the limit as x approaches 2 of g of x. Take those two limits separately and then we'll multiply them. So if I plug a 2 into the formula for f, I get 3. And then my limit as x approaches 2 of g of x. So let's see, here's x equals 2. Put a little ant. I might have to make this a little bit bigger. Okay, so my little ants are going like this, approaching at my x value of 2. What is the y value there? Um, Looks like it's about 1. We can double check by plugging in, right? That's the formula for the line. If I plug a 2 in there, I do get 1. Okay, so this is 3 times 1, which is 3. Okay, last one. The limit as x approaches -1 of f of x over g of x plus 2. So I have a quotient. I can go ahead and break up all of these limits. So this is going to be the limit as x approaches -1 of f of x over the limit as x approaches -1 of g of x plus the limit as x approaches -1 of 2. Assuming I don't get a denominator of 0, this should all be fine. Okay, so the limit as x approaches -1 of f of x. So I'm just going to plug a -1 in here. So that's going to give me 2 plus 4 is 6 plus 3 is 9. And then the limit as x approaches -1 of g of x. So here's -1, go a little to the left, a little to the right. Looks like my y values are approaching 0. 0 plus the limit as x approaches -1 of 2 is 2. So that comes out to 9 halves.